Assalamu alaikum. I'm Tavinda Yasin. Today we are going to start the lecture number 25 for the classical mechanics. Today's our topic is canonical transformation. That is the topic previously related. We already started discussing the canonical transformations. Canonical transformation means that we transfer from the old coordinate system to a new coordinate system. That is more generalized and that can be interchanged from the new to the old as well. That canonical transformation is from the topic topic is from the classical mechanics of the BS 5th with the course codes PHY 509. Moving to the next point, we're going to start from the contents, the canonical transformation, in which we're going to discuss about the theorem and the example. Then what is the generating function. Then we are going to discuss the four results: result 1, result 2, result 3 and result 4 of the canonical transformation. And in the last we have some of the references to follow. We are going to start canonical transformation. For a given system of particles, we can define different sets of generalized coordinates. A transformation between two sets of generalized coordinates is called a canonical transformation if it leaves the Hamilton's equations invariant, that when we convert the old coordinate system to the new coordinate system, in this the Hamilton's equations are invariant. Suppose we have two variables qi generalized coordinate and pi is one set of generalized coordinates and generalized momenta. Capital H is the Hamiltonian of the system. Then we have the Hamiltonian equations: partial h over partial pi is equal to qi dot and partial h over partial qi is equal to minus pi. Suppose that capital Qi and capital Pi is another set of generalized coordinates and generalized momenta. Then the transformation from the old coordinate small qi pi to the new coordinate new set of variables capital Qi and Pi is called a canonical transformation. If there exists a function h naught called the Hamiltonian of the system with the coordinates capital Qi Pi satisfying the equations, then the new Hamiltonian equation will become the old Hamiltonian was represented by only capital H and the new Hamiltonian is represented as a h naught. So we can write partial h naught over partial pi is equal to capital Qi dot and partial h naught over partial capital Qi is equal to minus capital Pi. Starting with the theorem, the first theorem states that the transformation of old coordinate qi pi to the new old coordinate to the new coordinate capital Qi capital Pi is canonical if summation I pi dqi minus capital Pi d capital Qi is an exact differential, such that first example show that the following transformation of 1 degree of freedom is canonical. We have an example here where capital P is equal to 1 by 2 into p small p square plus q square. These are the old coordinates, and capital Q is equal to tan inverse of small q over small p. Now we're going to start the solution. Since capital Q is tan inverse of tan q over p, small q over p, we get after differentiating dq is equal to 1 over 1 plus q over p whole square into p dq minus q dp over p square. That will become p dq small minus q dp divided by p square plus q square after taking the LCM. As we know that summation I pi dqi minus capital Pi dq capital Qi is equal to P dq minus P capital P dq. So after substituting the value, we have P dq minus 1 over 2 into P square plus Q square, substituting the value for capital P and then substituting the value of d capital Q, P dq minus Q dp over P square plus Q square. That gives P dq minus 1 by 2, cancelling P square, cancelling these two terms, we get P dq minus 1 by 2 P dq minus Q dp, and after opening that equation, P dq minus 1 by 2 P dq plus Q dp, and taking the LCM and solving, 1 by 2 is here, then that becomes 1 by 2 PDQ plus 1 by 2 QDP, and taking 1 by 2 common, we get is equal to 1 by 2 PDQ plus QDP. And from here the solution for that equation is equal to 1 by 2 into differential of 1 by 2 PQ. So the transformation is canonical, as that equation can be solved to get the above equation, and the above equation with the coordinates can solve that equation. Now there is an example such that show that the transformation capital P is log of sin P and capital Q is Q tan P is canonical. Now going to start the solution, we have capital Q is equal to small q tan small p. Differentiating that equation, we get dq is equal to d into q tan p, then tan of p dq plus q as it is, and tan p have the differential form secant square p into dp. As we know that p dq minus p capital Q is equal to p dq, substituting the value of p, we have log of sin p into tan, and then substituting value of dq, we have tan p dq plus q secant square p dp. Then rearranging the equation, we have p minus small p minus log of sin p tan p bracket dq minus q log of sin p secant square p dp. Since d over dp into p minus log of sin p into tan p is equal to 1 minus tan p cos of p over sin p, by solving that is minus log of sin p secant square p. From that we get log of sin p into secant square p, then p dq p capital D capital Q is equal to d into p minus log of sin p tan p. So the transformation is canonical. That shows that the transformation is canonical.
Canonical transformation, some related properties of the canonical transformation, and how a canonical transformation in general help us solving the equation of motion. Now we have already studied Hamilton's equation of motion, which are and These Hamilton's equation of motion do not actually reduce the complexity that we have seen with Euler-Lagrange equations. So for example, we have for a system which has n generalized coordinates, we had n number of second order differential equation which are Euler-Lagrange equations. And in case of Hamilton's equation, we have simpler first order equations, and but their total number is 2n, of course. Now if you substitute or reduce the variables, get rid of the momenta, then this Hamilton's equation essentially reduces to Euler-Lagrange equation. So in a way, we have not gained much, one can say, by devising these equations, the Hamilton's equation. But we note one thing, that if we change our variable from, say, one generalized coordinate and momenta set to another generalized coordinate and momenta, then it might be possible the equations become simpler. So for example, suppose from small q p to we go to the capital Q and capital P, such that the new Hamiltonian, it is essentially a function of only p's, like p1, p2. So in other words, this is the new Hamiltonian is a completely cyclic for all q's. Suppose we can choose such a coordinate, then what happens? Then this equations becomes extremely simple. So for example, because the coordinates are cyclic, all coordinates, so we can immediately write the pj dot. This is one set of equation, which is of course 0 because of the cyclic coordinates. So which means these are constants. Okay. Now the other equation is this will also be constant. In this case, let us suppose this Hamiltonian, as we have written, it's not a function of time. So Hamiltonian is a constant of motion. It's not an explicit function of time, and also it's not a function of coordinate. So partial derivative with respect to p's, and the p's being constant, they are also conserved. So essentially, after carrying out the partial derivative, we will get some constant coefficients. Now if these are constants, then the solution of qj as a function of time, it is trivial. Here the beta j's are, we get them from initial condition at t equal to 0, so qj is equal to beta j. Now you see, we have solved the equation, Hamilton's equation. The only catch is, our requirement was, this new Hamiltonian must not be a function of time, it must be a constant of motion. And second requirement was, we have to cleverly choose the q's and p's such that in terms of the new coordinate, the new Hamiltonian becomes cyclic in generalized coordinates. So this is one big advantage. If we can do that consistently for all problems for which Hamiltonian is constant of motion, which fortunately happens for many physical systems, then we can use this solution. So one just have to choose a special set of coordinates, and this lecture will try to look at how do you choose, rather how do you go from one old set of coordinate to a new set of coordinate. Let us suppose that we have a Hamiltonian which is a function of some generalized coordinates and corresponding momenta and time. And now suppose that we would like to move on to a new set of coordinates with capital Q, capital P, such that we will have a new Hamiltonian. We'll denote it by K, and often, like Goldstein, we will call it jocularly Hamiltonian. So this Hamiltonian would be function of new coordinates, and Hamiltonian is of course function of the old coordinates, and we are moving from the old coordinates to the new coordinates. The motivation of such transformation is already described, that often we try to make the equation simple by choosing coordinates in which the new Hamiltonian become kind of cyclic. So this Hamiltonian could be just function of p's and not q's. So we can make such a choice. The question is, in general, how do we transform? I mean, how do we go from old coordinates, old momenta, to new coordinate, new momenta? And we would like to explore or understand the rules and the methods rather. Now, using the old coordinate, we can always demand that the modified Hamilton's principle that must hold, which means that so as the system moves from point 1 to point 2 and we consider all possible paths, and if we look at the variations along these paths of the integrand, then about the correct path or the true path, the variation vanishes. This is the modified Hamilton's principle, the statement. Now, it holds for the old coordinate, and if it does, then you already know that from this we got our equations of motion, which are now if we have a canonical coordinates, a new pair, I mean new set, then we can equally demand that for this new set we must have and this will give us similarly so the question is, if the left hand side holds, so that means the modified Hamilton's principle works with old set of coordinates and new set of coordinates, then what can we say about the integrands in these two integrals? The answer is straightforward. We can say that these integrals, they can differ by a multiplicative constant plus we can always have a total time derivative of a function added to one side, and this function in general, it could be a function of q and the new coordinate and time. Now, why it is so? I mean, let's look at that. First, let's disregard this one. Okay, let's focus only on the multiplicative constant. Now, one thing is clear. When both the equation vanish, you can say that the integrand is of such a nature, the variation vanishes, the variation about the true path vanishes. Now, if you scale each of these p's and q's such that you get the new set of coordinates, then of course the true path will not change just by because you are only making some scaling transformation. let's look at it more carefully. For the time being, we shall ignore this the additive function. Suppose we define Pj to be like just a multiple of the old coordinate. Let's say beta is fixed for all pj's, and similarly let us suppose we do this. So we are basically scaling the old coordinates by some numbers to get our new coordinates. If we do that, then we already had this in terms of the new coordinates would be what? 1 by alpha qj dot is equal to yes. So I just substituted, because alpha and beta are constant, just substituted small q and small p in terms of capital Q and capital P, and what I get is so similarly the other equation would be so if you define k to be alpha beta h, then you see, the new equation is basically just a scaling factor away. The Hamiltonian is just scaled by this factor alpha beta. So for that, the scaling transformation will look like, alpha beta times pj qj dot minus h. It holds for the above transformation. It always works, and this alpha beta you can define it to be lambda. So which means a simple scaling of the coordinates will always give you a new set of coordinates where Hamiltonian simply gets scaled by the product of those scaling factors. So such transformation where we are just multiplying individual coordinates or momenta by a factor are called scale transformations. Scale transformations are not difficult. It's simple. Now, these transformations in general for which this relation holds, we call them in general, they are transformation. If the lambda is not equal to 1, we call them extended canonical transformation. And if lambda equal to 1, then we just call them a simply canonical transformation. Okay. Now, all right. So we will, for the remaining part, we will focus on canonical transformation, which means we shall assume the lambda is 1. For the other cases, extended canonical transformation, it's extremely simple. If you have some q's and p's, original set given, then you can move on to a new set using this function, which we still have to describe what it is and what does it do. But anyway, suppose you move from qp to some another intermediate generalized coordinates and momenta by adding a function df dt of this form, and after that you can do the scaling, or you can first do the scaling from old coordinate to an intermediate set, and from the intermediate set you can move on to the new set by adding this function. In any case, let us have a look at what this function does. I will rewrite the modified Hamilton's principle once more. And yes, now if you remember, when we were deriving this equation, we were considering different paths. Then from point 1 to point 2, we demanded that in the configuration space, the Qj, they have no variation at the endpoint. And the moment we assume that for the new coordinates the same principle holds, then that also means even for the new coordinate, the variation at the endpoints are not allowed. Okay. Now suppose we have a function, in general a function like this, and then if you add total time derivative of this function to this integrand, say, so that means now it looks like this is what it looks like. Let's focus on the last term, and that is essentially the last term is d of f. After all, the dt, it's a integral of time and its total time derivative, so it's simple. So we are evaluating the variation of f at the endpoint at 1 and 2. Now suppose f is let me move it here. Okay, now let us suppose the f is a function of some small q, capital Q, and time. Let us suppose it's like this. In that case, I can, when we calculate the df dt or we calculate the d of f, that can be written in terms of the new coordinates, because that is what matters in this integrand, because here the small q's are not important. Small q's are parameter as far as this particular variation is concerned, and the relevant quantity is the capital Q, which becomes the generalized coordinate. Now df can be written in this form, and you evaluate this particular term only at the endpoint. So basically we are looking at the variation at the endpoint of delta qj times del f del qj. So we are essentially considering this. After taking the delta and taking it inside, this is what we have. Now this quantity vanishes simply because we just mentioned that delta qj, that can't have any variation at the endpoint by demand. We demanded that at 1 and 2, so these vanish. So which means that if you have a function of a small q, capital Q, and t, and that you are adding with one of the integrands, then that leaves the essentially the integral unchanged. Okay, that's very important. So that means that two integrals can differ by total derivative of a function without any problem. That is possible. That is possible. So the canonical transformations, we shall say that the new coordinates and old coordinates are related in this fashion, where f is a function of, let's say, old coordinates, new coordinates, and time. Remember, when I say coordinate, I mean coordinate, not the momenta. For momenta, we will have a slightly different form. We'll discuss that later. Now, for such functions where only the generalized coordinates appear, they are historically called f1. So we will stick with this notation, f1. Now this condition, if it is true, then we can expand it. We can expand the total time derivative of f1 as and the left hand side is of course there. Now you see this function, f1 is functions of q's, small q's and capital q's, and they can be varied independently, and their coefficients, time derivative of qj, small qj and capital qj, must individually match on both sides of the equation. So which means that this pj and qj dot and this quantity, from there we can say that why we are doing this. I mean, I'll just repeat once more that we are demanding that qj's and small qj's and capital qj's, they are separately independent. As far as this function goes, it's like a function of x and y and something else, let's say t. Now x and y can be separately varied, independently varied. If that is the case, then the coefficient of x dot and coefficient of y dot must match on both sides of the equation. So this is why we are doing this for qj dot, and similarly we'll do that for capital qj dot, and that will give us also we will have that's it. So what we can say is, if we have an appropriate function given in terms of the old and new coordinates, then it's easy to construct the remaining variables. For example, the old momentum, we can easily construct it as del f1 del qj, and then we have the new momentum which is given by minus del f1 del capital qj, and the new Hamiltonian or the Hamiltonian would be the Hamiltonian plus the partial derivative of f1 with respect to time. Now how does it help? Meaning, how do you completely move on from old coordinates to new coordinates? After all, if you look at this set of equations, these are but mixture, in the sense that f1 is a function of small q and capital Q. Here too you have small q and capital Q. The answer is, you start with this last equation. Say for example, this one, where you have now this is a function of the capital Q's and small q's, etc. And what you can do is, you can substitute, you can invert this relation to get q's, let's say, in terms of the new coordinates and new momentum and time. So you see, you have the old coordinates, new momentum and time. Now invert this relation, all these equations, algebraically invert it to get the old coordinate in terms of the new coordinate and new momentum. And then you have another set of equation where once you have done it, then you can simply substitute that in the first equation. The first equation, in the sense that this particular equation which I have written again. If you substitute it here, then what you have is, after substitution, these pj's will now be a function of q's and p's, because already you substituted small q, you have written small q in terms of capital Q and capital P, new coordinates. So right hand side you can do the same. So once you have the old coordinates expressed in terms of the new coordinates, then it is straightforward. K is h, the old coordinates, plus del f1 del t. Here too you have to substitute the small q and small p. You can do that, it's already done above. I mean, you know the expression in terms of the new coordinates. You substitute that, and here too f1 has the old coordinate, that too you can substitute. Then the entire right hand side would be in terms of the new coordinates, and that's it. So you got your new Hamiltonian using the new coordinates, and from there you hope, I mean, for a suitable choice of f1, you hope that you have got the right coordinates, which will make your equations much simpler. Maybe if you have a good f1, it can make your Hamiltonian cyclic in capital Q, in which case the problem is extremely easy to solve, almost trivial to solve. In some cases, it is useful to work with not a function which are functions of old coordinates and new coordinates, but to work with a function which is a function of old coordinate and new momentum. I mean, often we find this is particularly useful form. Now, if you look at f1 and f2, they are nothing but Legendre transform of each other. I mean, basically we are moving from one function to another, such that remember one requirement of Legendre equation. I mean, we already got it, that this must still be true. In any case, we will derive that. But we demand basically that these two be Legendre transform of each other. I mean, then we leave it here, and then suppose we can do this, that f1 would be f2 minus, that's it. This would be I'm writing this one from the Legendre transformation, where the common variables are q's and p's. Okay, so we subtract the product of q and p, and that connects f1 and f2. If we do that, then we already had but f1 is f2 minus qj and pj, so we will write that, and this would be now remember f2 is a function of old coordinate, new momentum and time. So that gives us so you can see the first term cancels, and from the remaining term we have to match the coefficients. If we match the coefficient of small qj, then we get back the relation that we were demanding earlier. So it follows from from the matching of the coefficients, and then for the capital Qj, the relation would be different now. It would be I think we made a mistake here, because it's a function of pj's. It's a function of pj. Yeah. So I mean, this is fine. So we are matching the coefficient of pj dot that gives us Qj must be equal to del F2 del Pj. Yeah, so that's what we, and the remaining part we still have to write the Hamiltonian, and that would be, yeah, that would be just exactly what we had before. That's it. So I mean, for the sake of completeness, I write down the remaining relation. Here too, when you move from one set to another, you will have to invert a set of equation so that you can write small pj in terms of, I mean, the new coordinates. It's basically useful to invert always the coordinate, always the, first you choose this equation where the new coordinates appear on the left, so which means the Qj equal to del F2 del Pj. Now this is a function of Q, capital P and T. So if you invert that, you get the old coordinate in terms of the new coordinates, and then you can substitute that in the remaining equation to get the old momenta in terms of new coordinate and momenta, and then these can be substituted in H to construct K. H and F2, you can substitute that and then construct K, and then the problem solved, in the sense that you have everything in terms of the new variables. Now we can try to look at some simple examples. For example, suppose F1 is given, it's not a function of time, and this is the function. Then what would be the, I mean, the new momentum and the old momentum and the Hamiltonian? We can easily construct that. Say for example, F1 is this, so we derived it just now. So Pj is equal to del F1 del Qj, and that gives us, so Pj is equal to minus capital Qj. So it looks like we are interchanging the coordinates. And what about the other part? And that's it. So you see, we are basically going from, I mean, we can say that so we just interchanged the role of position and momentum. So our new momentum is the old coordinate, and new coordinate is basically the old momentum. So it is possible, and this basically very clearly shows, in fact, that why we repeatedly mention that the position and momenta in Hamiltonian formalism are just names. I mean, they enjoy the same status. So you can just choose another set of coordinates where the two quantity, the position or the coordinate and momenta, they just interchange there. The roles are interchanged. So this is one example. Now look at another example. Here what we have is F2 is a function of old coordinate and new momenta, and given by this product, and of course there is a sum over j, which we are not mentioning most of the time. So what about the coordinates here? Well, The momenta is easy to calculate. It does not change. The new momenta is same as old one. And what about the new coordinate? It's same. So basically, this is nothing but identity transformation. The new coordinates are same as old coordinate. This is just a exercise just to show. I mean that one can move from, one can interchange the definition. Coordinate becomes momentum. Momentum becomes coordinate. Or I mean certain transformations possible which leave the equation of motion unchanged. Of course.
Now we're going to discuss about what is the generating function. Generating function is an important function that is used in the canonical transformation. The transformation QI to the new coordinate capital QI is canonical provided that there is a function capital G called the generating function satisfying d by dt into G. dg over dt is equal to L for Lagrangian into Qi dot t minus L capital Q, that is the new Lagrange, L into capital capital Qi dot time, where L's are the Lagrangians with respect to the old and new variables, that are the old variables and that are the new variables. We can express the generating function capital G using one of the two old variables and one of the two new variables. We can make a combination using two old variables and then using the two new variables we can make a new set of generating function. Here that is the set, that is the old coordinate QIPI, old variables QIPI, and that capital QIPI at the new set. Now we're going to start the result one. When the generating function capital G is expressed using small qi capital Qi and t, it is denoted by capital T, and we get pi is equal to partial t over small qi, and capital pi is will be equal to minus partial t over partial capital Qi is equal to and h naught will be equal to h plus partial t over partial small t time. Proof of the result is as capital T is equal to capital T into Qi old variable and a new variable capital Qi to T. Differentiating that equation, we have dt is equal to summation I j is equal to 1 to n bracket partial t or partial Qi dqi plus partial t or partial capital Qi dqi plus partial t or partial t dt. That giving that equation number 1. We have to use that equation next. Further, dt by dt is equal to L into Qi dot t minus capital L capital Qi dot t, and summation, then summation pi Qi dot minus h is minus summation, that is the old variable Lagrange, so that is the new function, and generate for the new variables to be converted minus, that will become summation pi Qi dot plus h naught, as there is the minus sign so there is the plus sign, so dt is equal to summation pi dqi dot summation pi dqi minus h dt summation p dqi plus h naught dt, that is equation number 2. Now we're going to start with the next example such that show that the following transformation is canonical and find the generating function in terms of p and q. We have p is equal to 1 by 2 p square plus q square and capital Q is equal to tan inverse of q over p. Solution. Canonical part is easy. By rewriting, the given transformation becomes P is equal to Q cot T Q, and capital P is equal to 1 by 2 Q square cosecant square capital Q. The equation Pi is equal to partial T over partial Qi becomes partial T over partial Q is equal to Q cot capital Q. By integrating the partially with respect to small q, we get capital T is equal to 1 over 2 q square cot capital Q plus function of f of q. The other equation capital Pi is equal to minus partial T over partial capital Qi becomes capital P is equal to minus partial T over partial Q, and hence minus is equal to minus partial T over partial Q, that will become equal to minus partial over partial Q, substituting the value of T 1 by 2 Q square cot Q plus for f of Q, that value substituted here. So we have 1 by 2 Q square cosecant square Q plus d by dq f of Q. We have applied partial here and here. As we know that d by dq f of Q will be equal to 0. So f of Q is equal to, after integrating, is equal to C, that is the integration constant. So we can write capital T is equal to minus Q capital Q plus C. So the generating function is capital T is equal to 1 over 2 Q square cot Q, neglecting the constant. Now we are going to start with the result 2. When the generating function capital G is expressed using small qi pi and it is denoted by S, so we have capital Pi, small pi is equal to partial capital S, so S over partial small qi, capital Qi is equal to partial S over partial Pi, and H naught will be equal to H plus partial capital T over partial T. Proof of the result we are going to start with S is equal to S of Qi, that is a new function with the variables Qi capital Pit. Then dt will be equal to summation j is equal to 1 to n summation n partial S over partial Qi dqi plus partial S over partial capital Pi dpi plus partial S over partial t dt. Giving that equation number 1. Then further differentiating with respect to g, or the generating function will be equal to dg over dt is equal to old variable minus new variable Lagrange, so that will be equal to partial summation pi qi minus h minus summation pi qi dot plus h naught. Then we have summation into p dqi plus capital Qi d capital Pi minus summation capital Qi dpi plus pi dqi in plus h naught minus h dt. d by dt g plus summation qi dpi plus pi dqi is equal to summation pi dqi plus qi dpi plus h naught minus h dt, and that gives ds is equal to summation pi dqi plus q capital Qi d capital Pi into plus h naught minus h dt. That is equation number 2. Now from equation 1 and equation 2 gives us small pi is equal to partial S over partial Qi, and capital Qi is equal to partial S over partial capital Pi, and h naught is equal to h plus partial S over partial t, such that for the canonical transformation p is equal to log of sin p and capital Q is equal to small q tan p. Find the generating function in terms of p and q. This is another example. We're going to start the solution here. P is equal to sine inverse of e power p, and capital Q is equal to q tan sine into sine inverse of exponential p. By integrating partially with respect to q, we get sine inverse of p. Above first equation becomes partial s over partial small q is equal to p, that is equal to sine inverse exponential p. By integrating partially with respect to q, we get s is equal to q sine inverse of exponential p plus f of pt. The other equation, capital Qi is equal to partial t, capital T or partial pi, becomes capital Q is equal to partial s over partial p, and hence small q is equal to exponential p over under root 1 minus e square e 2p exponential power 2p is equal to capital Q, and from here that is equal to partial s over partial capital P. That gives small q into exponential p over under root 1 minus exponential 2p plus partial over partial p function of pt. As we know that partial over partial pf of pt is equal to 0. So f of pt is equal to f of t. So the generating function is sine s is equal to q sine inverse of exponential p plus f of pt, and neglecting the constant result 3, we are going to start the another result, that is the result 3. When the generating function capital G is expressed using the capital Qi, Pi and T, it is denoted by capital U, and we get small q is equal to minus partial U or partial Pi, and capital Pi is equal to partial U or partial capital Qi, and H naught is equal to H plus partial T and H partial U over partial T. Proof of the result is we have the new function U is equal to U Pi Qi capital Qit. Differentiating, we get du is equal to summation I j is equal to 1 to n into partial u over partial pi dpi plus partial u or partial capital Qi dqi plus partial u or partial d dt. Giving that equation number 1, we have dg by dt, the generating function, that is equal to old variable L qi dot t minus new variable L into capital qi dot t, then summation pi qi dot minus h minus into summation pi capital Qi dot plus h naught, then d by dt into g minus summation into pi small qi summation into minus qi dpi minus pi dqi plus h naught minus h dt. Du is equal to summation into minus qi dpi minus pi dqi plus h naught minus h dt, that is equation number 2. Equation 1 and equation 2 gives us small qi is equal to minus partial capital U or partial small pi, and p capital Pi is equal to minus partial U or partial capital Qi, and h naught is equal to h plus partial s over partial t. So now, and that is the solution of the problem. Does there exist a generating function p is equal to q and q is equal to minus p of the form g capital G is equal to capital G p q t for the transformation? Now we're going to start the result for when the generating function capital G is represented using the capital Pi small p and time t, it is denoted by capital P. So we get Qi is equal to minus partial V or partial Pi, capital Qi is equal to partial U or partial Pi, and H naught is equal to H plus partial T or partial T. Now starting with the proof of this result, V is equal to V into Pi comma capital PIT, and differentiating we get d V is equal to summation j is equal to 1 to n partial V over partial Pi dpi plus partial V over partial capital Pi dpi plus partial V over partial t dt. That is you mistakenly written here, that is V here. Dg by dt is equal to L into dq qi dot t minus L into qi dot t, set of old and new variables interchangeable. So then summation pi qi dot minus h minus summation pi qi plus h naught, then d by dt into G plus summation pi capital QI minus pi small qi is equal to summation into minus qi dpi plus qi capital QI dpi dot plus into h naught minus h dt. Then dv is equal to summation into minus qi dpi plus capital QI dpi plus h naught h minus dt. That is the equation number 2. From equation 1 and 2 gives us summation qi is equal to minus partial v of partial small pi, capital QI is equal to partial v of partial capital pi, and h naught is equal to h plus partial s over partial t. Now find the generating function of the transformation pi qi in comma capital QI is equal to p pi.
Generating function. For that, first of all, we will see some of the generating functions and their respective derivatives. Generating function derivatives. So, what are the possible generating functions? Generating function could be a function of small q and capital Q. This function can be differentiated with respect to small q and capital Q. So we have two formulas, and capital P is equals to minus of del f by del capital Q. It is obvious that this function can be differentiated with respect to small q, and this function can be differentiated with respect to capital Q. So these are the formula you have to remember. Now a generating function can also be a function of small q and capital P, and therefrom we have two formulae. P is equals to del f by del Q, and capital Q is equals to del f, here it's plus, it's not minus, by del capital P. Again we could have a generating function which is a function of small p capital Q, and here we could have Q is minus del f by del small p, and capital P is equals to minus del f by del capital Q. And again, fourth type of generating function that is possible is a function of small p and capital P. Then again we have two formula, that small q is minus del f by del small p, and capital Q is del f by del capital P. You see the pattern here, that whenever it is differentiated with small q, it gives us small p. With respect to small p, it gives us small q. When function is different with respect to capital Q, it gives capital P. When difference with respect to capital P, it gives capital Q. So this is the pattern that you have to remember, and that capital P is always minus and small q is always minus. This is you have to remember. Now in some textbooks you would also find that this could be written as f1, so this should be written f1 f1 2, so this can be written as f2, otherwise not important in a certain problem. f3 f3 f3, and it is generally written as f4 f4 f4. Now what is the use of generating function and these formulas? These formulas, this formulae can give us the interrelation between the old coordinates and momentums with the new coordinates and new momentums. Thus we could have the new Hamiltonian by substituting those values into the old Hamiltonian. So in our problem, the generating function is the function of small q capital Q, and this is the function. So we will see that this matches with this. it's a function of generating function small q of small q and capital Q, and we will be using these two functions and find out the relations between the old coordinates and momenta with the new coordinates and momenta and substitute it in the old Hamiltonian. So let us see it. Okay, one more thing, that this f1, f2, f3, f4, all these, actually f2 can be found out from f1 using Legendre transformation, f3 can be found from f1 using Legendre transformation, and f4 can be found using Legendre transformation from f1. So Legendre transformation is something that you have to see from some textbooks.
I dot. The lecture is continued here. We are going to start from here next in the next lecture. If there is any kind of difficulty regarding the topic canonical transformation, which is very important, as well important with the uh, aspect of your final your exams. So thank you. These are the references you can follow if there is any difficulty in the topic, or otherwise you can ask me by in the next lecture, so that I will be able to clear and make you clear all the topic and lecture. Thank you so much. Allah Hafiz.